Welcome back. Now we'll discuss about the coagulation practices in this module. Previously, we were talking about the plane sedimentation and what are the principles of plane sedimentation. Then, what are the practices and how to design the sedimentation tank, all those things. So here, the coagulation is one mechanism which is used to settle down the finer particles. The plane sedimentation removes only coarser and discrete particles. The fine sized particle settling, it takes a longer time. So what we have to have is we should have a mechanism which will help in reducing the settling time. For that, we are adding some chemical which is called as a coagulant, and the process is called as a coagulation. So now what you are seeing in this picture, so we are adding a coagulant here and the number of impurities are there, and where the colloidal particles which are having less than 1 micron size are also available in this. So now the thing is the coagulant will have both positive ions and negative ions. The first thing what we have to do is we have to separate the positive ions from the coagulant. So now you can see this mechanism. Suppose you are adding aluminum hydroxide or alum. So alum is having aluminum as the positive ions. So aluminum positive ions are now separated from the alum, and these colloids, they are mainly negatively charged. So these positive ions will get attached to these colloidal particles. That is how the separation process is going to occur at the first stage. So these positive ions of aluminum, so they will get attached to these negative charged particles. And next step is now we'll try to make some other modification in the operation process. That is a slow mixing. So in this slow mixing, what will happen? Whatever the particles which are attached, they will come closer together, and they will get attached into a bigger mass because the aluminum flock, whatever is formed here, it is gelatinous, so it's sticky precipitates, so it will easily attract the particles which are very near to it, so it becomes a bigger mass. The third operation is we will keep it without any disturbance. So there the heavier particles sorry, will get settled down to the bottom of the tank. So there are three mechanisms. One, we are adding a chemical here, the coagulant, and then we are making a rapid mixing here. Why we are doing rapid mixing is to dissociate positive ions from the coagulant into the water to get attached to the negative charged colloidal particles. And second step, we're going for slow rotation. So all the attached particles will come closer here, and subsequently they will form into a bigger mass. And third stage, we are having a sedimentation where all heavier particles are removed. So in this process, what we are seeing is the size of the particles will get changed from step 1 to step 2, step 2 to step 3. So that's why they are called as flocculent settling or type 2 settling, because the size and the shape of the particles, they will be changing due to settling in the sedimentation tank. The discrete particles we are referring as the size and shape do not change. There are flocculent particles, they have their size and shape getting changed due to coagulation process. Now, if you see different types of coagulant normally used, alum is the common name, aluminum sulfate is the main chemical name, chlorinated copperas, ferrous sulfate and lime, magnesium carbonate and lime, polyelectrolytes. These are some of the common coagulants which are used. The mechanism of reset, quick release of positive ions into water from coagulants, which are immediately sticking with colloids. And slow mixing, we are adding so that all the sticky particles are gathered to form bigger mass. Third one is settling of the bigger mass. So if you look at the settling size of the particles, now you see here up to 1 mm is okay, less than 10 microns after 2 hours. Okay, less than 2 hours up to 10 microns. But if you're going to smaller sizes, it's going to years and days. This is where the coagulation practices will help in improving the settling of the particles. And what you see the factors, what type of coagulant we are using, a number of coagulants are there. And then each of the coagulants have their different reactions with water, and they depend upon the pH of the water and what type of mixing you are going to use, how much the rotation speed, at what speed the positive ions are quickly released. Those type of factors we have to understand. How much is the dosage of the coagulant, how much you have to add, 5 ml, 5 milligram per liter, 10 milligram per liter. It all depends on the impurities which are present. The impurities are particularly, they contribute towards the turbidity. So higher is the turbidity, higher is the requirement of coagulation. That is a simple thumb rule. So major particles will be settled on the plain sedimentation, but often in the water treatment plant, the plain sedimentation and coagulation, they do not occur separately, but usually the sedimentation is now uh, coupled with the coagulation practices. And reaction of the coagulant, and what is the alkalinity of the water, because the reaction of the coagulant with water depends sometimes on the alkalinity, that is the pH or the nature of the water. Temperature is a reaction, so higher is the temperature, higher is the reaction. And how much time you are retaining the coagulant with the water in the first phase, the second phase, the third phase, and what types of impurities. Now you can see the impurity, different types of impurities are there. They are depending on different sizes here. So this is how the coagulation practices work. Now we will try to understand what is the procedure to find out how much amount of coagulant is required. This is called is optimum coagulant dose test. We normally go for the jar test apparatus. The jar test apparatus, what we see here, we are having a number of jars. So it can be 4 to 6 jars, usually 1 liter of volume. We can keep water in this sample water whose um, turbidity is high, which you want to remove the turbidity at the number of solids, quantity of solids here. We normally go up to 500 ml or 1 liter water in the samples here. This is a beaker we are going to keep. And now we are having a attachment here where they can see the shaft and their blades are there. We can insert it through a screw and then we can insert all the things into the water. Now you are having a two setups here. One is a time controller and then is a speed controller. So what we'll do is once we keep the sample in the jars, we'll add different amounts of coagulants, say C1, C2, C3, etc. So for example, I take 1 liter of water here, I add 10 milligrams of alum here, 20 milligrams, 30 milligrams, 40 milligrams. So the concentration is 10 milligram in 1 liter, 20 milligram in 1 liter, 30 milligram in 1 liter. So like that we are having. So now what is the first step in the mechanism? You have to have a rapid mixing. So we have to adjust the rapid mixing controller. The mixing is a rotation speed controller, and we have to keep it at highest RPM, more than 100 RPM. And the contact time will be around 20 to 40 seconds. We set the time and then we'll operate it. So the blades will be rotating at high speed, and this will ensure the quick release of positive ions from the aluminum positive ions from the alum into the water. So that is the first step is over. After fixed time, maybe 30 seconds if you are selecting. After 30 seconds, the dissociation is over now. And after that, we will go to the rotation controller here, RPM controller, and then we will make it at a lesser RPM, say maybe around 20 to 30 RPM, less than that. And then the contact time is around 20 to 40 minutes. So let us assume that we operate it for 20 minutes. And then these blades will be rotating for slow rotation for about 20 minutes time. In this process, what will happen? All the attached particles will come closer and then form into bigger mass. So remember, as long as rotation goes on, all these attached particles under suspension. So now we will go to the third stage. The third stage, what will happen? We'll stop the rotation and allow for settling for around 90 minutes and allow all the particles to settle down. So ultimately what will happen? The particles will settle down, clear water goes up. So we will take the clear water from each of the jars and we will test for turbidity. Say T1, T2, T3, and T4. Initially, whatever the sample you are taking into the jar, that also should be checked for turbidity. Let us say it is T. So T minus T1 will be the turbidity removal in the jar 1. T minus T2 will be the turbidity removal in the jar 2, like that. So if you want to remove the percentage efficiency, say in first jar, T minus T1 divided by T into 100. So ultimately what we will do, we will identify the jar in which the higher amount of turbidity is removed. Turbidity is nothing but presence of suspended solids. These solids can be larger solids or finer solids. Larger solids, anyhow, they will be removed, but finer solids, they will be removed through the aid of coagulation. So this is how we are going to use the jar test to identify the optimum amount of coagulant to be used. Normally, how we have to use this is in regular days, a lean period, the water quality is almost the same. That is, we will not have to change much of the coagulant dosage. But in rainy season, the flood waters will come. It will have a lot of impurities in the water. So we need to remove most of the impurities in the water before it goes to the next treatment operation. So here the coagulant dose will be regularly changed. So this is where we have to regularly check the turbidity removal using the coagulant dose. And we have to use the jar test more frequently, and regularly we have to monitor how much amount of coagulant is to be added for effective treatment of removal of these suspended solids in the raw, right? So this is about the jar test. This is how we are going to use in the laboratory to find out the optimum dose of the coagulation. So let us quickly look at the chemistry of a coagulation. Aluminum sulfate is a hydrated salt, Al2SO4 thrice, 18H2O. So you can see here when alum is added, having a molecular weight of 662 grams, it will react with the calcium bicarbonate, natural alkalinity, 3 into 162 grams, to produce aluminum hydroxide, say 78 grams of aluminum hydroxide and 2 moles, 2 into 78 grams, plus calcium sulfate plus water and carbon dioxide. So if calcium bicarbonate, natural alkalinity is not available, then we will add lime. So how you are going to add this lime? So lime in terms of calcium hydroxide we are going to add. So 662 grams of alum and then 3 moles of hydrated lime, 3 into 74 grams, is going to give you, this is aluminum hydroxide. How you are going to produce this hydrated lime? Then from the dry lime, you add water and then you're going to get hydrated lime. 56 grams of dry lime is now equal to 74 grams of calcium hydroxide. Similarly, 3 moles of hydrated lime is required for 1 mole of alum, right? And another thing is 3 moles of hydrated lime is equivalent to 3 moles of this natural alkalinity, which is equivalent to 1 mole of alum. So this is what we have to understand in the equality relationships. And the 662 grams of alum produces 2 moles of aluminum hydroxide, 2 into 78. So 156 grams of aluminum hydroxide as the sludge. You want to calculate the sludge, you have to use this relationship to calculate the quantity of the sludge. So now what about the pH dependence? So this is useful in the range of 6.5 to 8.5 pH. So most of the waters are within this range. So therefore, we don't have to add the improve or add or improve the acidity or alkalinity in the water. So usual dosage around 10 to 30 milligrams per liter. 30 milligrams per liter mainly during high turbid conditions in rainy season, and 10 milligram per liter is the normal concentration in the normal seasons. It reduces taste and odor in addition to turbidity of the water. It is cheap and the flock formed is quite tough to be broken easily. It provides crystal clear water. The only disadvantage is the sludge is gelatinous, so difficult to separate it from the water. Now let us look at the chlorinated copperas. Chlorinated copperas is the general term, but the chemical name is hydrated ferrous sulfate, FeSO4 7H2O. So it is oxidized to ferric sulfate and ferric chloride before adding as a coagulant. So now what you see here, the reaction, the ferrous sulfate you are adding and then reacting with chlorine in the water, converting into chlorinated copperas. These two are the combinations, nothing but chlorinated copperas. You have to add these combination as for the coagulation practices. This ferric sulfate here, you can see calcium hydroxide, hydroxide alkalinity reacting to calcium sulfate and ferric hydroxide. This ferric hydroxide is the sludge which is formed in this reaction. Similarly, ferric chloride reacts with calcium hydroxide alkalinity to convert to corresponding chlorides in ferric hydroxide. Sorry. Here, the only thing is we are adding ferric salts. The sludge is slightly heavy. And what you see is the ferric chloride is effective in the range of 3.5 to 6.5 and above 8.5 and used independently. We can use independently or combination. Ferric sulfate is in the range of 4 to 7 and above 9. So here the raising or lowering of the pH is essential when you are adding this type of coagulations. So now another one is ferrous sulfate or copperous. So ferrous sulfate and you have to add a lime also to that. So you have to add ferrous sulfate and lime. How you're going to have here? Ferrous sulfate and lime, you're going to get ferrous hydroxide. This ferrous hydroxide participate in the reaction to get ferric hydroxide as the sludge, right? So ferric hydroxide is gelatinous flock and heavier than that formed due to alum. Effective pH range is greater than 8.5. The normal pH of the water is around 6.5 to 8.5. So here you require the rising of acidity in the water, rising of pH in the water. Then polyelectrolytes. So they are the synthetic electrolytes which are developed and they are available commercially. They're available commercially. And they are nothing but a high molecular weight water soluble polymers. They are classified as anionic, cationic, and non-ionic, depending on the charge they carry. Cationic polyelectrolytes are independently used as effective coagulants, while others are used in addition with the alum. So normally we are going to use the cationic polyelectrolytes in the water treatment system because they can be independently used, right? So the cationic polyelectrolytes which are available are Flocalian, Magnifloc, Mogul 90, 980, etc. The dosage of polyelectrolyte is very small, up to, for example, 1 milligram per liter. Whereas in alum, you are seeing 10 to 30 milligrams per liter. So a small amount is required and available cheap. So it doesn't have much of complicated reactions. The sludge produced also will be less. The use of polyelectrolytes not only broadens the pH range over which a satisfactory flocculation occurs, but also requires the conventional coagulant reductions. The dosage is around only 1 milligram per liter. So that's why wherever possible, the polyelectrolytes are used to reduce the cost of coagulate and the amount of sludge to be handled during coagulation practices. Now there is a debate which is better, iron salts or alum salts. Alum salts, what you see there in the discussion we have seen, they are operated under a pH range of 6.5 to 8.5 natural pH. And iron salts, they are have to operating at different pH ranges. So where we have to balance the pH of the water, which is another complicated process. The sludge formed here is slightly higher, heavier in the iron salts compared to alum. And the other one is uh, the iron salts produces some amount of corrosion in the pipes which are carrying. So the alum is preferred because there's no corrosion and no additional skill. Why additional skill means pH balancing, such type of things are not required here. So iron salt, the advantage is unless if you are maintaining the pH of the water, it can be used at a wide range of pH. But we have to balance the pH of the water wherever the salts are being used. Iron salts can also remove taste and odor as well as hydrogen sulfide. Iron salts can cause corrosiveness than that by alum salts. Handling of iron salts require more skill, where no skill is required in handling alum. The time required for flock formation, conditioning, and settling using iron salts is less. Detention time is reduced. The advantage is only detention time, but the operational problems are slightly difficult to balance when you are using alum as a coagulant. So that's why in normally water treatment, alum is used in the coagulation practices because of some simple advantages over the uh, iron salts which are available for the purpose. Okay, that's all for now in the coagulation practices. In the next video, we'll go for seeing small calculations and operation of different units, unit operations, which are used under coagulation practices. Thank you.